Hello, I'm Mike McCulloch. Today I thought I'd explain why I'm so confident about quantized inertia. It's because I've spent 20 years publishing papers giving the evidence for it, collecting and giving that evidence. So I thought today I would list the evidence so you can see how widespread it is. So I'm going to do it from the cosmic scale downwards, so ordered by scale. So the first one is the cosmic acceleration. The cosmos is apparently, according to observations, accelerating away from itself, which standard physics cannot explain. Well, quantized inertia does explain that. It explains the numerical acceleration at the edge of the cosmos, which is 2 × 10⁻⁻10 meters per second, although I would not say that the acceleration is actually a physical one, but it's something more subtle. But it predicts the numbers. The cosmic flatness problem, it's been noticed that the cosmos is almost closed, so it has about as much kinetic energy as it has potential energy, and quantized inertia explains that as well, and I explained that in a previous video. The low LCMB anomaly, the cosmic microwave background is far too smooth on the largest scales, and that is explained by quantized inertia because on those scales patterns do not fit within the Hubble horizon or the cosmic horizon. QI gives the first explanation for inertial mass, first mechanistic one, which is a gradient in unirradiation felt by an accelerating object. It gives an explanation for, or at least predicts, the Hubble tension as well, which is this same very small acceleration. QI gives us a value for G. You can derive G from cosmological parameters. And that's because in quantized inertia, any volume must contain enough mass within it so that the underwaves seen by the accelerated objects of that mass are smaller, shorter than the cosmos itself. And in that way you can predict G, the gravitational constant. And it predicts a change of G with time as well, which can be tested. QI explains the galaxy rotation problem, the observation that galaxies, especially at their edges, are spinning far too rapidly to stay bound, given the amount of matter they apparently possess. And quantized inertia explains that by reducing the inertial mass of the stars at the edge of the galaxies, and with no adjustable parameters or anything like that. It explains wide binary orbits, so wide binary stars orbit each other far too rapidly for standard physics, and quantized inertia explains this in the same way by a loss of inertial mass from the stars, and it explains it exactly and without adjustment. It explains the orbiter Proxima Centauri, which is the closest star to us, and which is orbiting around Alpha and Beta too fast for standard physics without them looking at extreme solutions. Quantized inertia predicts this orbit without extreme solutions. It predicts the, well, this is a controversial one, but it predicts the Pioneer anomaly and the Ulysses anomaly, which is of the same size. But with that one, there's also a rival thermal explanation. QI predicts the flyby anomalies, which are speed boosts seen in spacecraft flying by the Earth. So it predicts those quite well. It predicts relativistic jets, and also interesting variations in laboratory measurements of G. They seem to be predicted by quantized inertia as well, though there is a factor of 4 involved there, which there's some uncertainty there. So coming down to the smaller scale now, there is a way to predict cold fusion, or LENR, low energy nuclear reactions, from quantized inertia. It inspires a kind of, quantized inertia inspires a view of time which can help to explain the EPR, Einstein-Podolsky-Rosen paradox. There were some tests done on supercooled spinning disks by Timar in Germany, and QI explains those very well as well, very accurately. There was power generated from an asymmetric cavity by model, and QI explains that as well. There were thrusts seen in capacitor tests, also in a lab we had in Plymouth, which quantized inertia predicts very well, including the exact dependence on the plate spacing of the capacitors. The quantized inertia also predicts the result of Podkletnov in an interesting way, where he spanned superconducting disks and noticed that gravity appeared to vary very slightly, and also the M drive as well. So the fact that microwaves resonating within conical cavities seem to thrust very slightly towards the narrow end. Quantized inertia predicts that as well. So that's quite a long list, and I've probably missed off quite a few things. Almost all of these have been published in good journals, some of them several times over, and yeah, so that's a list. So I hope you've enjoyed this short, and looking at the scenery as well, which is we have a beautiful day today, and I look forward to speaking to you next time. Goodbye.